Hi all, welcome to Improving Cloud Scale Hardware Fault Diagnostic session. I'm Rama, working at Microsoft as a firmware engineer in Azure infrastructure team. My colleague Neeraj is co-presenting along with me. I will be discussing about hardware component level fault diagnostics, and Neeraj will be discussing about fault diagnostics for system level issues. Here is the high-level agenda. I'll be going over current challenges and requirements, then discuss about key learnings and solution options for component level hardware fault diagnostics. Neeraj will cover a case study on autonomous system dumps to do diagnostics of some of the system level issues. Let's start with challenges. Like cloud hardware consists of heterogeneous hardware fleet to support compute, storage, and machine learning workloads. This hardware comes from multiple system vendors and component vendors. I see the challenges in terms of three main areas. One is cost, availability, and tools. The costs come from whenever after the fault diagnostic happens, when you send the components to suppliers, they always complain that there is high replacement rate and no issue found when they do the failure analysis. This challenge mainly comes from lack of clear and comprehensive error reporting by firmware or software when they detect some errors. Second challenge, I see server availability. What I mean is when there is a new hardware failure happens with cloud scale workloads, production workloads, it takes long lead time to identify mitigation and solutions. This mainly comes from gaps in telemetry solutions to root cause new failures. The third challenge I see in terms of tools, many times as this hardware comes from multiple vendors, they report these errors in custom error log formats. Not based on all of them, not based on the standards. To understand this error logs, we end up being integrating multiple vendor tools to analyze the error. Sometimes these tools are not cloud ready in terms of security and compatibility with existing software. And also because of this error log formats are custom, whenever we try to do error pattern analytics using machine learning tools to do the failure prediction and to try to move the workloads, if we predict that there is a problem, this leads to some challenges because there is a lack of consistency and gaps in the solution, the way we report the error, and amount of telemetry data available. As we've seen the challenges, let's look at some of the requirements to do better diagnostics at cloud scale. The cloud hardware has CPUs, memory, network storage devices, and FPGA and other devices to support different workloads. First requirement is having a clear and comprehensive failure signature for each type of hardware error. Second, having a high telemetry data to quickly root cause new failures happens at cloud scale with some production workloads. The third thing I see is ability to do the autonomous and near real-time fault diagnostics. This is very critical because some of the issues only happen at a cloud scale with production workloads. Those issues may not happen at a lab environment. To support ease of tools, we need to have a standard-based error reporting. Let's look at the existing standards, why we have like a custom error log formats. For out of band, where we use a BMC cell log to report errors, like currently there is IPMI specification. This specification is a 20-year-old and it doesn't support all new types of hardware errors. And also the cell log is very primitive way of reporting hardware errors. It only has like 16 bytes of data. It's not sufficient to report full comprehensive error reporting. Like the in-band agents like host.os and UEFI firmware started using common platform error record. This is a UEFI and ACPI standard based. Okay. And before I discuss about the solution options, I want to show some example to understand this problem in detail. Let's look at the DIM failures, how they are reported is out of band and in band. Like the DIM failure can happen at a row level, bank level, rank level, even at a memory controller level. For out of band, we use IPMI based cell log currently to report the error, as the IPMI cell has only 16 bytes of data. Mostly we just report as there is an uncorrectable ECC error happened, DIM 11. That is not sufficient to root cause what kind of problem with the DIM, so that it helps with the component suppliers to come up with a solution by working with cloud vendors. Whereas in band, as you see, it has a in details about the error. It has details about the bit position, row column, device, even the physical address, which helps to root cause the problem quickly. In summary, out of band error handling requires improvements in the way the error reporting should happen. Let's go back to the what customers and cloud vendors did to come up with this limitation. Like we started adding like custom cell logs, some system crash dumps to enhance the telemetry required to report this. And also started using wider adoption of CPER by like UEFI firmware and host.os to give more data. But out of band error reporting is very critical to support kind of bare metal scenarios and new edge kind of workloads, and also like sometimes when system failure happens, in-band agents may not be available. That's why we need to standardize this out of band error reporting. Some of the solution options are like for out of band, use the error format is similar to the CPER, which is spec defined. And as an industry, we need to work with DMTF to define redfish schema for all hardware error types, because IPMI spec is become very old there is no maintenance on the spec. We need to work with DMTF to define this. And when in-band agents report errors to BMC can map these records to Redfish logs. And also, I see the great opportunity to standardize this outbound error formats, as there are current open BMC firmware initiatives. There is a plan to form a subgroup along with Facebook and Intel to work on productizing these solutions. Please join this work group to provide a feedback. Thank you all. I will hand over to Neeraj to discuss about system level fault diagnostics. Thank you.
To OCP, and my name is Neeraj. I work with Microsoft Cloud Manageability team, and in the second session of the talk, we'll be focusing on some of the cloud diagnostic challenges and requirements. So just to give you some background, as part of the manageability team, some of the challenges that we face on our day-to-day work is how to report a fault in a consistent manner across a diversified hardware. And the second challenge is, once the fault is reported, how do we find out the exact reason for the fault and why the fault has occurred, so that we could take preventive measures to avoid this fault on our next iteration. So let's talk about some of the challenges on the same lines. So the first thing is fault reporting. I think Rama covered it pretty well, and the first track was, we are using BMC to report out the faults, and we are using standard protocols like IPMI and Redfish to report out these faults. And IPMI, particularly in nature, is pretty primitive, and all we have is 16 bytes to represent a fault, which does not provide any clear information on. There are a lot of faults which are not defined by IPMI spec, and also we are, even in the Redfish, there are some of the faults that are not defined. So that's the first challenge on how do we report a fault in a consistent manner. The second challenge is much bigger, and that's where the problem comes. Is once you have a fault, how do you actually identify what has caused the fault? For example, we work with a lot of partners on a cloud platforms like memory, SSDs, drives, and things to fail at scale. And when we take this fault signatures to our partners, the first thing they ask is, okay, do we have any additional steps to reproduce? How they can reproduce the issue so that they can have the system straight so they could debug, because that's the most critical stage, right? And unfortunately, some of the faults are so catastrophic that they cause system reset. And that's where the challenge comes, is that we need information at the time when the fault has occurred, so that we could provide this information. We can harvest this information to identify what has actually caused the error. That's the biggest challenge. That's the second challenge. I think third is not a challenge per se, but it is more of a step. It's like, once you have the signature and once you have the data, critical crash term data that is required for debug, I think applying a fix is fairly easy. So now we have understood some of the challenges, and now let's talk about some of the requirements and goals from the cloud diagnostic perspective. So I think the first and foremost requirement for the cloud is, of course, we need to improve survivability. So diagnostic tools and diagnostic methodologies are here so that we could improve survivability and reduce our downtime, because, as I said, the cloud number one requirement is availability. And the second, and this is actually very important with respect to diagnostics, the overall the goal of the diagnostic is basically to reduce the cost of operations and TCO of offering the cloud, especially if you see in this precedented time where we are all locked down. Imagine if we have a fault, and that if the fault requires somebody to fly in and actually collect some of the information by connecting some tools like ITPs or some debuggers, it's not possible. So we are sort of, we are thinking in the lines that any diagnostic solution that we apply, we should be able to harvest all the critical information with respect to system state, debug registers, debug logs remotely. So that's number one requirement. And also, like, the cost is important, because if the diagnostic solution is actually pointing out the wrong through, and then it is not accurate, you're actually adding more cost to your cloud operations. And the third important requirement is the fault diagnostics. Fault diagnostic, the systems that we're designing, this should be this should be thought as a design requirement when we build systems. For example, the PSU can fail, fans can fail. So design should basically account for those failures, and built-in redundancy should be in place to protect these faults. For example, you can have n+1 redundancy in the PSU, so that when PSU fail, the PSU should be still be able to operate within this spec. You have fans, and if the one fan, two fan failure, so again the system need to be designed with those faults in design. And the fourth requirement is, again, this is aligning to the TCO, is it should be autonomous diagnostic. So any fault, system should be able to detect the fault by itself. System should be able to identify what has caused the fault, and system should be able to autonomously should be able to collect the required debug information from the system. And that's critical. And then the next thing is that we have also applied is any diagnostic solutions that we do, that should run out of band. Basically, they should not rely your host state to debug and collect system information, because it is possible that your host is not available, due to maybe catastrophic loss, or maybe it is engaged in some sort of different workload. So that's where we are recommending that our diagnostic solution should be supported out of band. And the next thing, the last step is basically, again, aligning the same lines, that whatever diagnostic solution that we have, it should basically be able to cater a variety of hardwares like SSDs, NICs, GPU, PSUs, and FPGAs, things like that. So now we have talked about some of the requirements and challenges, and I want to talk about a case study of what we actually applied on our servers, and we were able to actually get a really good benefit from this. So I think, so if you see, this is a standard Intel architecture where you have processors connected to QPI. There's a BMC that connects to processor via PECI, and also BMC can talk to processors from IPMB using PECI proxy. And the thing is that the BMC is also connected to the processors via some of the GPIOs, and the GPIOs are asserted when the processor is going through some internal errors. So the BMC can monitor for those GPIOs, and whenever the processor is transiting into the error, BMC can get interrupt. BMC can then go read some of the critical registers over PECI or over PECI proxy from via ME, and harvest it and keep it in its persistent memory. And that's then in the later stage of the time, a remote service or in-band collection tool that actually can talk to BMC, read that information, and process it for harvesting. So that way you don't lose the critical stage. That way you don't have to connect a critical debug kind of ITPs on the CPUs to collect the information. Everything is sort of happen in autonomous way. That's what we call our autonomous system crash dump. So again, we talked about the dump collection happens through PECI proxy, or can happen directly PECI. Dump harvesting can happen using IPMI OEM extensions. Again, we are using pretty raw commands, and in this we are using IPMI blob basically to transfer the data from the BMC to the host. Or we could also use IPMI over LAN. We can also use IPMI Redfish extensions as a Redfish telemetry service. We can also use Redfish cell logs. That is again left to the service on how do you want to represent the fault, right? So with that, I would like to wrap this presentation by calling out some actions that we can take and we can all learn from here. So I would recommend you to basically go contribute to this project. There's a hardware management project that has been set up. It has a pretty rich collateral on the generalizing some of the faults. There's a open BMC platform telemetry work group where we talk about standardizing some of the faults in Redfish and a telemetry service. I would want to call out that due to some internal changes, this work group is sort of inactive for a few weeks, but there's certainly a plan to revive that effort, and we'll again come back with some of the changes that we are proposing. So with that, I want to thank you all for attending this talk, and if you have any questions, feel free to reach out to us. The contact information is put in the first slide, and happy to listen to you from you guys, and thank you and stay safe. Bye-bye.